All right, so in this video, we're actually going to be jumping back to this kind of cute farmer river crossing problem or riddle or whatever you want to call it. So in front of you, you can actually see that exact same little grid, and I'm drawing there. Okay, so if you stare at that thing, you're going to see that I took the exact same grid that we had last time, and I just basically threw away all of the English words that showed us how to kind of achieve the final solution. So the game in this one, again, was to start with everybody on the left-hand side and then slowly work down towards the right-hand side. And here's my sequence of rules that I had to do to get from the start all the way to the bottom. And that's exactly what we want to be thinking about, is that when I stare at this little process, I really want to be thinking about this as some type of random starting state that's then going to traverse through a whole bunch of other little states, ultimately ending up where I want to be. And that's the goal in all of this, is that we want to take all of this and somehow encode this in such a way that you and I don't actually have to think about these nice little paths, but we can let something else identify if this is actually going to achieve a valid solution. So that's where the computing aspect comes into play. But we have to get it to a stage where a machine can actually understand this overall process. So we got to teach it a little bit on how this process all works and what are the components that are going to all make it up, and then let the machine go like crazy. So what we need to do is we need to think about how we're actually going to encode some of the information. So the information here is going to be where everybody happens to live, as well as what are the rules of the game. How do I go from state to state? What are some valid states? And by valid, I mean, where am I going to have, the goat not eating the cabbage or the wolf not eating the goat? All of those kind of things that we need to teach it, as we have to avoid those things, and then we can let this whole process kind of sneak through and actually identify this valid solution. So one of the ways that we can easily encode some of this stuff, and maybe you've already kind of thought through how you would in particular implement this, but one of the cheap ways of doing this is to kind of identify these little lists that are going to have 4 components. So the 4 components are obviously going to be the farmer, the wolf, the goat, and the cabbage. And if you look at the very beginning, I somewhat suggestively identified the sides of this river by not east and west or left and right or A and B, but by side 0 and side 1. And the reason for that is that that's going to make a really easy little vector that's going to tell me where everything happens to live. So the farmer has 2 options. He can either be on the left-hand side or he can be on the right-hand side. The actual traveling down the middle, we're going to be incorporating through the use of these nice little arrows. So the states are going to be properly at the end of the movement, where is everything going to be? So everything has the option of either being on side 0 or side 1. So for example, this game starts with the farmer, the wolf, the goat, and the cabbage all hanging out on the left-hand side, which is side 0. So that's going to be stored as this nice little vector of 0, 0, 0, 0. After that, we know that the farmer and goat went on a cool little voyage together, and we're going to have the farmer and goat living on the right-hand side. So what that tells me is that they're both going to be on side 1. So I know that the farmer is going to be that first cell because that's what I've identified it as. And I know that the goat is then going to be in that third cell. So those are both going to tick up 1 to indicate that they've moved sides, whereas the wolf and the cabbage are actually going to be living on the left-hand side. One of the things to note that actually becomes kind of cute here is that you can look at that here. Is the idea is that you have the farmer and goat living on the right-hand side. Because you don't see a wolf or a cabbage, you know that they must be on the left-hand side. That's where this binary structure comes into play really nicely, is that you're either on side 0 or you are on side 1, and we're going to involve the transition as being the little arrows between them. What you can also do is you can look over here and you can see, well, if I have the wolf and the cabbage on the left side, so side 0, I know that farmer and goat must be on the right. Another example of that is, let's say here, so we got the farmer, the wolf, and the goat. So the farmer, the wolf, and the goat all living on side 1. Therefore, the cabbage must be on side 0, which it is. After the transition of farmer and goat moving to the left, what we're going to see is that the farmer, the goat, and the cabbage are all on side 0, which we most certainly have. So farmer, goat, and cabbage all living on the left-hand side. So we have this really nice binary representation for where everything happens to live. We have 4 little slots because we have 4 things in play. Obviously, if you wanted more things in play, you would just add additional spots, identifying where they're all going to be living. A couple really classic questions are going to emerge. The first of which is, okay, how many states are there? The idea is that we're going to have these things moving all around, so we know some things are going to be happening. We know that these things are all going to be stored as these nice little lists, and these lists are all going to have 4 entries, and those entries each have 2 options. They can either be 0 or they could be 1. So if you start to think about how many there are in total, you realize that this is just a counting problem, in that you have 2 choices for the first spot, so the farmer can be on side 0 or side 1. Then you know that the wolf has 2 options. It can either be on side 0 or it can be on side 1. The goat also has 2 options, and so does the cabbage. So what's going to happen here is that you're going to have 2 times 2 times 2 times 2, or 16 total possible states. And you very quickly realize that these states are really just going to be represented as these nice little binary strings. You're going to have 4 components, so you have 0, 0, 0, 0. That's going to be everybody on the left-hand side. And you know everybody on the right-hand side is just going to be 1, 1, 1, 1. Or we can view this as a nice little list to properly indicate where everything happens to be. So it makes sense that there'd be 16 possible states. A kicker here, though, is that not all of these states are actually reasonable. And by reasonable, I mean that there are some additional rules to the game that we're actually playing. Namely, if the goat and the cabbage are left alone, the goat's going to eat the cabbage. If the wolf and the goat are left alone or unsupervised, that is, the farmer's on the other side, the wolf's going to eat the goat. So what's going to happen is that of these 16 overall states, some of them are not going to be ones that we want to reach. Because if we enter one of those, something is going to be eaten, which means we do not solve the actual riddle. So if we present all 16 of these things, so again, here we have the nice binary structure. We got 0, 0, 0, 0, and then I'm just increasing the order. So 0, 0, 0, 1, 0, 0, 1, 0, and obviously that goes all the way down to my final state that I'm working towards, which is 1, 1, 1, 1. What ends up happening here is that if you look at this thing, there's some symmetry going on, but there is going to be some states that things are eaten. And those are the ones that I've actually identified in red. So I'm not going to go through all of those, but I'll kind of let you zoom in on some of them to see what I mean by that. If you look at this one right here, what happens is that the farmer and the wolf are on side 0. So again, it goes farmer, wolf, goat, cabbage. Should be like cheese or something. It'd be easier to say than cabbage. But anyway, the game was cabbage, so we're going to keep that in line. So this tells me that the farmer and the wolf are on the left-hand side, which is then going to say that the goat and the cabbage are on the right-hand side, and they don't have any farmer supervision, so the goat's going to eat the cabbage because there's nobody to tell the goat no. So that's a state that we want to avoid. You can also see a very similar state where if the farmer is on the left-hand side by himself, and I have the goat and the wolf and the cabbage all on the right-hand side, I might have the wolf eat the goat, or I might have the goat eat the cabbage. Something's getting eaten. Technically, it could just be the goat alive. You know, if the goat first eats if the goat first eats the cabbage and then the wolf eats the goat, there's a whole bunch of things being eaten. So that's a state that definitely something is being eaten. And then we also have the very similar one where it's the wolf and the goat hanging out on the right-hand side without the farmer. There's obviously the exact flip of those where the farmer is on the right-hand side and everybody else is going to have these incorrect pairings on the left-hand side. So of the 16 overall states, we know 6 of them are ones we want to avoid. So that leaves us with, 10 total states? And then we want to start to think about how these things are actually going to be connected. So you form this nice little graph, and then we're going to traverse these things, and you go from the starting point to the ending point, and hooray, you solved a nice little riddle. All right. So what that graph actually looks like is the following. So I've kind of stripped away all of the words and all of those kind of things to kind of see what's actually happening here. So what we start with is everybody having a party on the left-hand side. And then what's going to happen is that the goat gets brought across, and that's actually the only move that's technically valid that makes things nice. I mean, technically, if the farmer just leaves by himself, then something's getting eaten. And if the cabbage or wolf gets brought across, then the other pairings are going to involve some eaten as well. So if we bring the goat across, that's really the only reasonable first move. Everything else ends up in some amount of something being eaten. Well, then once the goat's on the other side, Well, your really only option, well, you could technically bring the goat back, but that's kind of silly because then you're back in the starting state. So if the farmer just goes back on his own, then we're here. So we have the wolf on the right-hand side and everything, or we have the goat on the right-hand side and everything is great. And here's where we technically get a fork in the road, in that there's two different solutions here. One of which is we can bring the wolf across. The other of which is we can bring the cabbage across. And those two roles are flip-flopped in that they more or less function the exact same, because at the end of this, we're going to have it where the wolf and the cabbage are on the right-hand side by themselves. So you can either take this path, which is the one that we did, or you can take the path where the cabbage goes across and you bring the wolf afterwards. So in any event, those both exist, and then at the very end, you bring the goat back across and you are in your happy final state, and this whole process actually works. So you can kind of see the number of moves that were required. You had to bring the goat, the farmer had to go back, you had to bring a wolf, you had to bring a goat, you had to bring a cabbage, the farmer back, and then ultimately the goat at the end. So a bunch of little steps, all of which were not so terrible to do. So that's one of the ways to at least kind of introduce this notion of how we would actually encode some of the information. So kind of storing the various states. Another thing that's going to be